Okay, what's the bearing capacity equation? First of all, you need to understand that this equation, now I'm presenting the equation from the Canadian Foundation Engineering Manual, which is the same as the CSA S619 or Canadian Highway Bridge Design. They are not the same. I'll show you the two equations now. But what I want you to understand is that this equation is derived for plane strain case. What's the meaning of plane strain? It means there's only strain along this plane, and there's no strains along the perpendicular direction. So that's the plane strain, which is basically the definition of the strip footing, and that's most of the 2D like software are using. They represent like a plane strain condition. So you have a plane strain and all the deformation along this plane. And you don't assume like deformation perpendicular to the direction or in the direction perpendicular to this plane or out of plane. That's why there are some factors, some other factor are added based on experimental data. Okay, so that's the bearing capacity equation, a lot of terms, but let's simplify three components. Cohesion term for the foundation below, for the soil below the footing. Surcharge component, the confinement from the above or the applied surcharge, and the beta, sorry, and the gamma term, or I call it the foundation below the DF or below the foundation term. So that's cohesion, that's friction below footing or soil below the foundation level, and this one is this one above the foundation level, or the confinement due to soil above the foundation level. Let's see what does each term mean. So C is the soil cohesion, and we mentioned that before. If you have sand, usually sand doesn't have cohesion. Just imagine you play on sand in somewhere on the beach, and they are not connected together somehow. There's that kind of cohesion. It's usually loose, and the particles are not adhesive to each other. So there's no cohesion. So sand usually doesn't have cohesion. So C equals 0, but clay does have cohesion. So C is not equal 0. That's the general case, okay? And then QS is a surcharge, and it's equal gamma. So surcharge above the foundation level. That's why I call it gamma above times the foundation depth. So any surcharge, that's the effective vertical stress at the foundation depth. So effective vertical stress means it's just the soil above the foundation level. So if you have water, you're gonna subtract gamma water from the gamma of the soil above the foundation level. And again, dF is the foundation depth from the ground surface to the underside of the footing. MB is the effective footing width, or they call it B prime, and we'll explain all the meaning of prime later, but it's the foundation depth width for now. And just to be more specific, it's the smallest or the least plane dimension of the footing after considering load eccentricity. Considering load eccentricity will give you the P prime. So the P prime usually equal the footing width P minus 2 times eccentricity. That's coming, but anyway, the footing width. So if you don't have eccentricities, it's just P, okay? So that's B, the footing width. Gamma, here over here, that's gamma below. So foundation soil below, soil below the foundation level, or we call it the foundation soil. It's unit weight, so it's kilonewton per meter cube. And the Q ultimate is the ultimate bearing capacity. NC, we have now some factors. So NC, NQ, and gamma are the bearing capacity factors. And they are just a straightforward relation between the friction angle and these factors, NC, NQ, and gamma. And we will notice that in gamma, does it change from one equation to another, but it'll show us in details later. But NC and NQ, they are very, very unified across the geotechnical engineering studies. SC, SQ, S gamma, and all with S. So S is just as a factor, so you can call that lambda. Some textbook calls that lambda Q or lambda C or whatever the name. It's the factors that take into account the shape factor. So modification factor for the foundation shape. So that's why it ends with S. And the C term, it does have SC and then S for the shape, and the Q term SQ, then S for the shape, and S gamma, then S for the shape. And that's very clear. I'll go to the second one. So C, I, Q, I, S, gamma, I. So I that does represent something, and that does represent modification factor for the inclined loads. And we'll come to for details how we can calculate, in details how we can calculate all of these factors in very high level details, or not very high level, it's in detailed matter or detailed manner. Okay, modification factor for inclined loads. For the C, it's SC, for the Q, it's SQ, for the gamma, it's S gamma. And then the DD is the depth factor, modification factor for the foundation depth. And it's just SC times D, like D, and then SQ, D, S gamma, D, and eventually, we have the modification factor for the sloping surface. So if the ground surface above the foundation is not vertical, it's sloped. So that's for surface slopes, that's beta. So SQ, SC, S gamma, all beta. And S delta if the foundation itself or if the base of the footing is inclined. Again, all of this is coming in details. So that's the equation of the Canadian Foundation Engineering Manual. And now I'll just show you the equation from the CSA, the Canadian Highway Bridge Design Code. I'll say it's the same. It's just instead of C, they call it SU, the undrained cohesion of the soil, and C and Q and gamma are the same. Q is QS and Q. And then instead of SC and IC, that's the shape factors in the C term and the inclination factor in the C term. So SC over here equal to SCS, that's the shape factor. And IC equal SCI. So that's why I'm telling you they are almost the same. And here in the CSA, they didn't mention anything about the depth factor, so they don't take into account the depth factor. However, you can take it, and they just don't account for sloping ground or base inclination. But if the footing is on a sloped ground, you need to account for that, and you need to add some other factors. And if the footing is inclined, you need to add the data, the delta as well. So these two factors does decrease the bearing capacity. The depth factor is usually increase the bearing capacity, but that's why it's fine if they don't consider it here because it's more conservative. But if they don't consider beta and delta, that will be a problem for you because basically you will calculate Q ultimate equal 100, but if you consider the sloping ground, it will be 50 or even 30. So it's significantly change. So that's the Canadian and the CSA. And the general equation is straightforward. Make it simple. Cohesion term with a lot of factors. By the way, that's crucial. So if you don't have shape factor, what's the meaning of you don't have shape factor? So the shape factor usually just to account for the LMB, because here we said plane strain, it means like a limited width over a long area, like B times L, and L is very large. So if it's a straight footing, there's no shape factor. So all of this will be 1. If there's no inclination, so all of the inclination loads will be 1. If there's no depth factor, so all of the depth factor is gonna equal 1. So basically no depth factor means there's no foundation depth. So basically the soil is above the foundation level. So the foundation or the footing is at the ground surface. So there's no embedment. If there's no sloping ground, so beta and Q and gamma, all of this with beta will be equal 1. If there's no inclination, so the last term all is gonna equal 1. So what I want to say, you might have all these 5 factors equal 1, and it does not affect the calculations at all. So you're gonna add them if you have them in your problem, in your real life example. If you don't have them, it's fine. It's just 1. So straightforward. Now let's go to the H2. So H2 does update the bearing capacity equation a little bit. By the way, that's the general equation, and most of the factors over here from 2 scientists that are common, like they are very famous in the bearing capacity equations. But here, the H2 used Monfaka et al. 2001 equation, which is this equation. And as we mentioned, H2 is using ultimate limit state, and that's why they call it Qn as a bearing resistance. Nominal bearing resistance, that's what the H2 calls the ultimate bearing capacity. It's same thing, but here you'll see 3 terms again. Bearing capacity is always 3 terms. Cohesion term, surcharge term above the foundation level, and the friction or gamma below the foundation level. So C and C, same shape factor inclination, gamma Q full foundation depth. That's QS, by the way, because effective pressure is gamma times dF, but here they just call it gamma times d instead of using QS. And Q, shape factor, inclination factor, depth factor is just applied to this term, to the surcharge above. You will not find the depth factor over here. You will not find a shape factor over here, and you will not find the depth factor. Sorry, you will not find depth factor over here, and you will not find depth factor over here. Here S times, that shouldn't be delta, that should be gamma. So I'm gonna update that when you receive this presentation, it will be gamma. And in gamma, that's a function of the friction angle, I gamma, C, W gamma, and C W Q. Now let's stop for a minute. So all the terms are known for us. We have the shape factor, depth factor, inclination factor, shape factor, inclination factor, shape factor, inclination factor, NC, NQ, and gamma. We know all of these. So now we have CWQ and CW gamma. So that's basically to account for the water. So to account for the water in the H2 equation, you just add a factor, which is CWQ or CW gamma. The Canadian till now, we didn't see how you're gonna account for the water in your calculations, but over here it's straightforward. Just use this factor. I'll come to this later. So C is cohesion, gamma Q dF equal QS effective vertical stress at the foundation. Beta is effective width, least plane dimension on the footing after considering load eccentricity. To be more specific, this needs to be P prime, not just P. Gamma F, gamma foundation, foundation soil, and its unit weight, so it's kilonewton per meter cube, and Qn is nominal bearing resistance, as we mentioned before. NC, NQ, and gamma are the bearing capacity factors, direct relation with phi, and here in the H2, you will notice coming later that the N gamma in the H2 is different than the N gamma from the Canadian either Foundation Engineering Manual or CSA, but NC and NQ are the same. Shape factor for the cohesion terms, this needs to be C. So SC, SQ, S gamma, IC, IQ, I gamma, inclination, and then depth factor. And you just notice that depth factor is just applied for the surcharge load. And that's fine. Again, we said the depth factor is extra, so it does increase your bearing capacity. So if you take it from here and from here, it means you are giving a more conservative solution. So ideally, overall, the depth factor in the H2 is not applied to the foundation term or to the cohesion term. And CWQ and CW gamma are correction factors to account for the location of the groundwater table. All of this is coming in detail. That's a very high level. If after this equation, I just want you to know that we have three parameters: C term, as a charge term, and foundation term, or below term, or gamma term. So CQ and gamma, C and C, Q, S and Q, half or 0.5 gamma P, and then we have other factors, shape factor, inclination factor, depth factor, and whatever factors we have in our problem or in our real life.